In this illustration, we'll analyze a rotating rod on a sleeve. Here we are given that on a smooth rod PQ, a sleeve A of mass M can smoothly slide, and a thin uniform rod of mass M and length L is hinged at one end, which can rotate in the plane of this figure on a sleeve, and it is kept in the vertical position as shown in figure. And it is saying if the system is released from rest, we are required to find the velocity of sleeve when the rod rotates by 180 degree. So in this situation, if we release the system from this position, the rod starts rotating, and here we can see if this is the situation when here you can see the rod becomes vertical. In this situation, and this sleeve A. So when the rod, if we consider, was rotating from the right side, and this rod is moving at an angular speed omega, we can consider that the sleeve would be moving toward right with the velocity v2, and we can consider v1 as the velocity of center of mass of this rod. As no external horizontal forces acting on the system, the linear momentum of system must remain zero because initially it was released from rest. So here we can write in the situation, by conservation of linear momentum, here we use as the mass of rod and a sleeve both are equal. That means here V1 should be equals to V2, as the center of mass of the system must be horizontally at rest. Also, if the center of rod is moving toward left with the velocity V1, it is rotating at angular velocity omega, then the velocity of this point of rod which is attached to sleeve can be given as L by 2 omega minus V1, and that should be equals to V2. So we can write by constraint relation between rod and sleeve, we use, in this situation we can write L by 2 omega minus V1 should be equals to V2, as one point will have one speed only. And we can also write by work energy theorem, we have initial kinetic energy of system was 0, plus when the rod has fallen down by 180 degree, its center of mass is displaced down by 2L multiplied by 1 by 2, as its center of mass was at L by 2 and this has fallen down by L by 2. So this will be mgl, must be the final kinetic energy of the system, which we can give for the sleeve. It is half m v2 square, and this v1 equals to v2 we can substitute as v. So in this situation it is half m v2 square, plus for the rod it is half m v1 square, plus the rotational energy which is half ml square by 12 multiplied by omega square. So from this relation, if we substitute v1 is equals to v2 is equals to v, say, then in this situation on substituting the values we get mgl is equals to mv square plus this ml square by 24 multiplied by omega square. And the value of omega you can see from this relation we are getting this 4v by L. And if we substitute the value of omega over here, we can see the value of v, the velocity of sleeve, or v2, is given by root of 3gl by 5. That is the result of this problem.